Fine, so we have question 3. Define specific heat capacity. Well, specific heat capacity comes from this formula over here, mc change in T. So obviously if we rearrange that, we have C is equal to Q divided by M change in T. So it's going to be a joule per kilogram per Kelvin. So it is the energy required to heat or to change the temperature of 1 kilogram per 1 degree Celsius. Okay, the energy required to change the temperature of a substance by 1 Kelvin per kilogram. Something to that effect. This one over here, 2 equal masses of 2 different solid substances. So we've got 2 equal masses, 2 different solid substance A and B are at the same temperature. The specific heat capacity of substance A is greater than the specific heat capacity of substance B. The two substances now have their temperatures raised by the same amount. Explain which substance will have the greater increase in internal energy, assuming that both remain in the solid phase. Well, you know that your internal energy, we can call it U, is made up of both the potential energy and the kinetic energy. So if they remain as a solid phase, basically the potential energy of each of them is going to remain the same. But as you raise the temperature, your kinetic energy is going to increase. This is what's going to go up. Your kinetic energy is going to increase. Now, because the specific heat capacity of A is greater than B, it's going to be a greater amount of energy per degree Celsius is going to have to be added to A than to B for the same temperature increase. And therefore, A will have a greater increase in the internal energy, greater increase in U, the internal energy. Okay, I hope that makes sense. You need to write that out nicely for your 2 marks there. Going on to this question here. It says, the diagram below shows part of the heating circuit of a domestic shower. So you have insulated wire, you have 240 volt supply, water pipe, and the cold water is coming in at 14 degrees Celsius, it's coming out at 40 degrees Celsius, and you've got your heating unit. So it says cold water enters the shower unit and flows over the insulated heating element. The heating element is rated as 7.2 kilowatts at 240 volts. Now, in actual fact, we don't need the 240 volts at all, but we do need this 7.2 kilowatts, or 7,200, so 7 times 10 to the 3 watts. We're going to use that. And we see that we have a change in temperature here. It goes from 14 to 40 degrees. And we have the specific heat capacity is 4.2 times 10 to the 3 joules per kilogram per Kelvin. So we have a change in temperature of our water it is going to be 26 degrees Celsius. So we want to estimate the flow rate of the water. So we're going to want to find a kilogram per second. We could also use a volume per second, but because we are given it in terms of we are given in terms here the specific heat capacity is per kilogram, that would be the best one. And we also have our mass, which is in kilograms. So we're going to basically use this formula over here. Q is equal to mc change in T. Now I have been given my power. Now we know that power is actually equal to Q over T. I can replace this watt over here by a joule per second. Okay, so I can have a joule per second term here, And when I work this all out, if I put in my power here, so if I work this out here, I have per second, for every second, I have got 7.2 times 10 to the 3 is equal to the mass. That's the number of joules in 1 second. I have 4,200 times by my 26. And when I work this out, I am going to get 0.066 kilograms. And that kilograms is per second, because this 7,200 joules is per second. So it's per second to the negative 1 will give me my rate of flow of water, of H2O. I hope that makes sense. It's really important to use this formula. Often we'll give it in terms of power. All electrical devices and so forth have got a power rating, which gives us an energy per time value, and you can use that often. Suggest one reason why your answer to C1 is only an estimate. Well, the most obvious one there is that we are assuming what? We are assuming that all the energy is used to heat up the water. But we know there would probably also be heating up the environment, the pipes and the air around the pipes and so forth. So that would be the one major obvious one. The flow of water also could change, which doesn't need to always be constant. So that could also be something else. Okay, thank you.